Okay, shall we start? Okay. Okay. All right. So there was another typo. What's the longest repeat length in this tunnel? So I said 4, I think, but I was mistaken. It's 5. So TAGAC is a repeat. Okay. So this example shows that if the read length is 5, and although the read length is not long enough to bridge the longest repeat, you can still be able to reconstruct this genome. Okay, and so let's go through this point a little bit more to see what's going on here. Okay, so this is a simplified, this is a detailed picture, and this is a simplified picture. Okay, so what I'm going to do is to simplify this picture a little bit more for my further discussion in the next few slides. I'm going to do a processing, a post-processing of this graph called condensing. So you can see that all these nodes, they point in only one direction. So there's no choice. Once you embark on this node, you have to keep going this direction. So you might as well just condense all these nodes together to form one big supernode, which is a concatenation of all these strings together. So I'm going to do that to simplify the graph. And I basically get this graph. Okay? So this graph is equivalent to this graph, except that I'm condensing all these nodes into one node, condensing all these nodes into one node, and condensing these two nodes together, because, again, there's no choice other than going this direction. Then you become this graph. Okay? There's one slight typo here, is that this node corresponds to the condensation of these nodes. So this node should really be on top of, this thing should be flipped around. But I somehow drew it wrongly, and I get this graph, condensed sequence graph. So using this representation, a unique Eulerian path goes like this. It goes down here and comes in a circle and comes back here. And this is corresponds to going this path. So let's see now why the interleaved repeat, the non-interleaved repeat. So here I have a non-interleaved repeat. Okay, so these two repeat, and the greedy algorithm. The greedy algorithm. What would the greedy algorithm do? Is that when a greedy algorithm, what it does is it merges nodes, basically locally. Okay. So therefore, it doesn't know that if it merges these nodes together, this edge and this edge together, to form a bigger contact, it doesn't know that it's committing a mistake. What the Eulerian path algorithm does is it looks at the global picture and finds this path instead. That's why the greedy algorithm is stuck by having long repeats. But the Eulerian algorithm gives you a global picture and was able to resolve them. Okay. All right. So now we understood entirely what happens in the dense read situation. The dense read situation corresponds to the case when you have a read at every starting position of the genome. Now we're going back to the shotgun sequencing model. In the shotgun sequencing model, you have reads randomly scattered, so you may not have a read starting at every single position. You may have a read here, a read here, a read here, and so forth. Okay. Now, the idea was to essentially mimic the dense read scenario by looking at k-mers of length LV. Okay? So the idea is that you want to create this situation, but you don't have the situation because you don't have that many reads. So the idea is you take your long reads of length L, and you look at all length K subsequences of each of the reads. And think of that as a new problem where the reads becomes k-mers, which are length K subsequences. So you think of these guys as your reads. Okay? And then you apply exactly what we did earlier, which is to construct the graph. And now each node of the graph is coming from the k-mers. And k is a number which is less than L. And then you find the Eulerian path. Okay? Now, let us think about the performance of this algorithm in terms of our plots. Okay? So when does this algorithm succeed? Well, it succeeds under two conditions. The first condition is that K should be larger than the critical reading, right? Because if K is not larger than critical reading, then this problem with k-mers is not going to reconstruct, right? So that's the first condition. So K should be L critical, which is that condition over there. Now, however, there's a further condition. There's a further condition. What's the further condition? Well, if you want these k-mers to span the whole genome, then that means the adjacent reads, the original reads, should satisfy a certain condition. So suppose your next read, suppose this is your first read of length L, and suppose this is the second read of length L. And the overlap between these two reads are small. Then when you extract the k-mers, can the k-mers span the entire genome? Suppose K is 100 here. And this overlap between this read and the next read is, let's say, 50. Then when you get down to here, then you cannot continue anymore because you don't have a next k-mer anymore from the next read. So therefore, you need some condition on how close the adjacent reads are in order for you to create a k-mer which can cover the entire genome. Can anyone tell me what's the condition you need? So I give you a k, let's say k equals 100. What do you need the reads to satisfy? The reads should overlap by at least 99 or 100, somewhere around there, right? I always miss it by 1. I hope you don't kill anyone by doing this. It's not my responsibility. I hope you guys bought flood insurance or something. Okay. So you need an overlap between genome or between reads of length K. This is what I call K coverage. Okay. So now you have to choose a K. So K is my design choice, right? So now I basically can choose K such as satisfy those two conditions. You give me a genome, you give me a coverage. So basically, you give me a read length L, okay? I optimize over K. To satisfy those two conditions. And then I choose N, the number of reads, so that both conditions are satisfied. Okay? That allows me to compute the curve. Okay? And the curve looks like this. the blue curve. Okay? So you can see that this blue curve actually reaches the vertical asymptote of the lower bound. That means as the number of reads go to infinity, that eventually it hit the lower bound. You can't really see it here, but believe me, when you plot this curve and you go up to the next floor of this building, you will hit that black curve. Okay? So asymptotically, as the number of reads go to infinity, the blue is good. However, for finite, for read lengths, the coverage required is much larger than the lower bound. So for example, if my read length is, let's say, 2500, which is about 10% larger than my critical read length, the coverage depth is about 5 times Leonard-Waterman. So that means I need 5 times more reads. So if Leonard-Waterman needs 100 million reads, I will need 500 million. Okay? And the reason for that is that actually I'm losing some information by doing this congruent approach. So what am I losing information about? Well, what am I doing here? I'm taking this read, say of length 1000. I'm chopping up into segments of length 100. And then I throw away the original read of length 1000. And then I try to reconstruct the genome using my reads of length, tables of length 100. I'm losing information. Why? Because these k-mers actually come from a longer read. If I throw away the original reads, I'm losing information. Because I no longer know that they belong to the same place. Right? So that's why there's a gap there, and the gap is coming from loss of information from the reads. Okay? So now the question is, how do I bring back the reads into this picture in an intelligent way in order for me to close the gap between the blue line and the black line? Okay? So let's see how this can be done. Okay. So here's the example. So I have an interleaved repeat here. Okay? And this is the Bruin graph condensed after condensation, which shows the situation. Okay. Now, if you look at this graph, I claim that by just looking at this k graph alone. So now I'm choosing k. So what am I choosing k? If I don't have any other information other than the k-mers, then I have to choose k to be at least as large as this number, right? Yes. But to have this large k, that means I have to have adjacent reads overlap by a lot. That means I need a huge amount of number of reads to be able to get so many reads so close together. Now I want to reduce my number of reads I need. Right? I want to go down this curve. To reduce the number of reads I need to cut down on k. I want to make k smaller than this number. So now I'm going to show you how I can make k to be smaller than this number. Interleaved repeat. I can still be able to reconstruct. Okay? So, since I choose k to be less than L interleaved, now on this graph, on the k-mer graph, it looks like this. So what is this picture? Let's understand this. So this node is repeated here. So this node actually represents these two copies. And this brown node represents these two copies. And I have incoming edge here, purple coming to here. This thing goes to either the green here or the purple here. And the brown goes to purple or light brown here. Exactly. So this is my condensed graph. And because I'm choosing k to be less than the interleaved repeat length, so let's say less than this length, brown length, you can see that the brown copy is not resolved. In other words, I have 2 guys coming in and 2 guys going out. Okay? So I don't know how to resolve this with this information. So I claim that with this picture, the number of the Eulerian path is not unique. Can anyone tell me I claim that there are 2 solutions. There are 2 Eulerian paths which goes through this graph. Which 2 are they? Let's start with this one. This is the beginning of this thing. This is definitely this guy. Now I have 2 possibilities, right? I could go up or I could go down. Let me go up first, and then come down here. Would I go from here? Go down, come back up. Would I go down from here? Go down, come back up. And this is one Eulerian path. What's the other solution? When I'm here, I could have come down here and then loop around and go up. So that's why there are 2 solutions. And that's why interleaved repeat poses a problem when I choose K to be less than L interleaved. But now I claim that I had actually a read. If I had a read that bridged at least one of these 2 copies, that was a necessary condition anyway. So assume I satisfy that, all right? Then I claim that actually I could figure out which of the 2 solutions is the correct. Let's see. So I have a read here. So what I can do is I can put this read on this part of the ground, because I know this read contains this brown thing, so it must be around here. Now this read bridges from the green to the light brown. So I also know that it must span this edge and then go to this edge. And it's not like this path, right? So now with this information, I can now further simplify this graph to get a unique solution. How? Well, because I know that this read goes here, then I know that whatever start here should go to this graph. So what I could do is I could create another copy of this guy. And this copy connects from the green to the light brown. And now this repeat is resolved by this bridging read. And now I can find the unique Eulerian path. What's the unique path? From here, down here, up, and then back up. So now I know that I will not be going up in the first shot. Because if I go up in the first shot, then I'll end up here and I'll be finished. I cannot span the whole graph. Okay? So this tells you how you can use the bridging read information to resolve one of the repeats. And then you use the unique Eulerian path to resolve the other leftover. And thereby resolving this interleaved repeat. Okay? Because in reality, the reads are long enough to resolve. It's only that this K-word graph trick that I use does not show it, but I bring back the read to explicitly improve the graph. Now, if I do that, then I get this curve. Okay? Now, yes?
The intersection is explicit epsilon probable curve, right? And all of the epsilon.
Yes. So these curves, I forgot to mention that. Thank you very much. All these curves are computed for a specific epsilon. Because when I do the calculation, or when you do the calculation in the PI, then you should calculate it with respect to a specific epsilon. I think in this example, 99% or 1% epsilon. Okay? Again, as I said, epsilon cannot be 0. Yes, help yourself, Professor. Help yourself. Then we don't need lunch. If we go long enough, we don't need lunch. Okay. Now, all right. So this curve is still not hitting the low band. So what is missing? So just to remind you what's happening here, I have now chosen my K to be less than L interleave. And I'll use my bridging interleave repeat read to resolve my interleave repeat that is apparent in this K. Why am I still a gap here? And what is limiting my choice of K right now? Well, I'm still choosing the K greater than L triple, right? Because if I choose K to be less than L triple, then I have triple nodes occurring. And I have not explained to you how I deal with the triple repeat node. So let us do that as one last step. Okay, so now I want to push forward. And now I have this triple repeat situation. Okay? So the triple repeat situation is the following. I have a triple copy, 3 copies of something. And what does it mean in terms of the graph? In terms of the graph locally, it looks like this. I have 1 copy here, which is repeat 3 times. Remember my K there. My K is greater than L triple. So this node is all merged together. It's like 3 copies of repeat all merged in 1 node. And you have 3 incoming pieces and 3 outgoing pieces. I don't know how to connect that. That's my confusion. But now I have a bridging read. Okay? So once I have a bridging read, then I know that I can go from here to here. And if I have bridging reads all over all 3 paths, okay, then I can do the same trick as before and break off these 3 nodes and resolve the repeat. All right. So at this point, you should be doubting what I'm telling you. There's a logical, there's a bit of fault. One is do you remember what was the necessary condition for triple repeat? This is really a test. What was the necessary condition for interleave repeat? I have 4 copies, right? What was my condition? Necessary condition? Let's go back. If you look at this picture, the necessary condition was 1 of the 4 copies to be bridged. I don't need to bridge 2 of the copies, I don't need to bridge 3 of the copies or 4 of the copies, just 1 of the copies. In a triple repeat case, the necessary condition is also bridging 1 of the 3 copies. But here I need to bridge all 3 copies. So therefore, I'm not meeting the lower bound. In fact, I'm requiring a stronger condition than the necessary condition. If I had only a condition which resolves which uses 1 of the 3 copies, then I meet the lower bound, and I'm tight, and I can call myself a success. Yeah, this is part of a very big graph here. I'm just showing a very small part of this thing. The whole thing is too complicated. But more generally, it doesn't have to be feedback, right? More generally, this could go to some other parts of the graph. The bridging is so maybe it's not matching this picture very well. Yeah. So maybe there's some colors throughout there. Yeah, there's some missing edges. But this is orthogonal to the point I want to make sure. The point is, do I really need all these 3 reads? Then I try to get by with fewer reads. Suppose I only have 2 of the 3. Is it enough? Suppose I have any 2 of these 3 reads. Is it enough? Well, suppose I have only the upper and the lower one. Well, if I have this read, then I can split off. I know this goes to here. And if I have this read, I can split off. So it seems that I don't need the 3rd read. It seems at least I can relax this condition to say 2 of the 3 reads, and therefore closer to one necessary condition. That's what we thought in the beginning. It turns out to be more complicated than that. So here's an example which says that if you have a triple repeat, then it is not so simple how to get a condition using only 2 of the 3 repeats. Okay? So here's an example. And suppose I only have, instead of, so here's this triple repeat, this node, 3 guys going in, but you don't immediately fork off at the output, but you fork off here, and then downstream, you split off. Okay, this is the cable. So I claim that, for example, if you only have this bridging read, and forget about the perfect green one, then it's not enough. Why is it not enough? So if you follow our early logic, then what we want is we want to break off this path to create a duplicate node so that you simplify the block, right? So the question is, without purple or green, can you actually take the blue and fork off this node here? Well, this guy comes in. At this point, if you fork off this guy, you don't know whether this guy is actually going here or going down here, right? So therefore, you cannot greedily split off this path. And so the problem is more complicated than that. And that is essentially our only gap in the solution. We needed, our condition was a triple copy, and we don't know how to reduce the number of bridges. Okay? Okay, so to summarize, this is the strongest theorem that we could prove. Maybe you could prove stronger. The theorem is the following: that the original sequence is reconstructible if all the triple repeats are all bridged, that is, all 3 copies are bridged, and all the interleaved repeats are singular bridged, only 1 copy of bridge is needed, and you have coverage of the geometry, of course you need coverage. Whereas the necessary condition for any algorithm is that the triple repeat are single bridge, and the interleaved repeat are single bridge, and the coverage. Okay? So we have a gap. But we got lucky with this particular data set, with this particular genome, because the upper bound and lower bound meets very closely. And so why is that? Well, it turns out that in this genome, the triple repeat is significantly shorter than the interleaved repeat. So therefore, the bottleneck condition is bridging the interleaved repeat and not bridging the triple repeat. Since the gap in our algorithm and the lower bound is in the bridging condition of triple repeat, it doesn't show up here because the triple repeat is much shorter than the repeat. So bridging that is very easy. So whether or not you need triple bridge or single bridge, it's the same thing. Pretty much the same thing. And we also got lucky in all these 3 benchmark data sets as well. To be honest, there are examples in which the gap is bigger. So this is an example of a case in which the triple repeat is of comparable length to the interleaved repeat. So that the lower bound induced by the triple repeat and the lower bound induced by the interleaved repeat, which is the black versus the dash, is very close. And now the multi-bridging is limited by the requirement to all bridge triple. And we see a gap. We tried very hard. We could not close it. Okay. Yeah.
Is there really a significant gap between bridging all 3 and bridging?
Okay. Here's a question. Is there a significant gap between triple bridging and single bridging, right? So in other words, the question is, do you need significantly more reads to triple bridge or not, right? And the answer is yes, you do. Because basically, to triple bridge, you basically have to hit all 3 spots. Whereas the single version only hit one of the three spots. So let me try to create a homework question on that. Okay? You do. Okay. All right. So, all right. So let me move to the second challenge. So how much time do I have now? Let's see how I'm doing in time. 11:15. Okay. So now what's going on?
So before it's wandering outside and then maybe so if that means like an umbrella. Take out the time.
It's thundering outside.
Yeah, take an umbrella and take some time.
Did I anger anybody with my talk? So that means I can talk as much as I can.
Well,
So what's the constraint of the lunch situation?
So I think 12:15, 12:20. If you have enough, leave it to talk or until then.
Okay, yeah, I have plenty more material. I can go to 2:00. But okay, all right. So then let me talk a little bit about read errors, because two things of interest here. One is there was a second challenge. So we have this jigsaw puzzle. So far we've been focused on how to deal with the repeats, right? And here it turns out that the fundamental thing is interleave repeat, triple repeat, and not simple repeats. So the second thing I want to do is in terms of read errors. So read errors is quite interesting for communication people like us, because communication is all about dealing with noise. And so now we're interested in understanding the impact of read noise or read errors on the performance of assembly. So what do I mean by read errors? So here's the model. So remember, each read is a randomly chosen subsequence of the genome. Okay. So before, I assume the read are perfectly noiseless. That means if you read, what you observe is identical to what is underlined. But since all this measurement thing is through some biochemical process, there may be a chance that when you read a G, it may become an A. Right? And so forth. Okay? So this is what I meant by read error. Okay? So you read a symbol, a nucleotide, it becomes another nucleotide. And the error rate, in other words, how frequent such errors occur, and the nature depends on the sequencing logic. Okay? All right. Example. In Illumina, the error rate is around 0.1 to 2% error rate. So that means if you have a read length of 100, you can expect many reads have at least one error. Okay, that would be a typical number to think about. And the errors are mainly substitution errors. That means G gets substituted to A. That's a substitution error. PacBio, on the other hand, remember, has very long reads. But it also has a huge amount of errors. 10 to 15% insertion, deletion. Okay? So the errors are more complicated because it involves, for example, you have a T and you get inserted another T by mistake. Okay? And the error rate is much higher. So you can see that if we want to take advantage of longer read lengths like PacBio, then we have to try to solve this problem of how to deal with errors. Okay? All right. So to understand the basic issues, I will focus on a simple model, and then I'll show you some simulation results on a more realistic situation. Okay. So here's a very simple model. The probability of a substitution is P. And once you substitute it with probability 1/3, 1/3, 1/3, the A, G, for example, will become one of the other two. So it's a symmetric noise model, and it's assumed to be independent from one symbol to another. Okay. So, What's the basic question one wants to ask in the setting? Okay. So remember what this number, L critical, for the noiseless case, right? When there is noise, do we think that L critical will change? That's the first question we want to ask. Because L critical is a number that we sort of get a very simple handle on. And after asking this question, we can ask, will the number of reads needed change with noise? Okay? So, what is L critical? L critical is next to this number. And now, with noise, what will happen to this L critical? You remember that I defined this L critical. So that's the question I want to ask. What is the impact of noise on L critical? Will L critical increase because of noise, or will it stay the same? So this question is equivalent to the following. Remember that in the dense read regime, which defines L critical, okay, the T quantity of interest is L spectrum. Okay? All right, quick reminder. What is L spectrum? Do you remember what L spectrum is? I take my genome. I look at every starting position of the genome. I collect a read from every position. I put all the reads together. That's my L spectrum. Now, what do I observe now? Well, I have read errors. So when I get a read, it may be noisy. Okay? However, I'm getting a lot of reads, right? Because in the dense read model, I allow the number of reads to go to infinity. So what do I want to estimate from my data? What do I observe? I observe 100, tens of hundreds of millions of noisy reads. What do I want to estimate from the noisy data? So this is now in a territory which is somewhat more familiar to us communication people. You observe a bunch of stuff noisy, but what do you want to recover in order to get back L critical? The spectrum, right? You want to recover the clean spectrum, which is the sequences and all the starting positions of the read.
So is the noise truly independent of the read? Like, are there certain read patterns which are more susceptible to noise than others?
Depends on the platform. In PAC-bar platform, the noise is quite independent of the content of the read. And in other platforms, the noise is also quite independent of the content read, but it may depend on the relative location of the read. So for example, maybe near the end of the read, the noise is higher. And in the very first symbol of the read, the noise is also pretty high. It's also higher. In fact, if you look at the so-called FASTQ file, which is the file format for the read data, the read not only comes with the cause, the AGCT, but also gives you a read quality, which is essentially how reliable that read is. And the quality may vary along the read length. In fact, if you remember a picture I showed for aluminum reads, the curve actually goes up. In fact, one reason why, and the main reason why the read length is short in some technology is because as you read on, the chance of getting errors are higher and higher, and until at some point it becomes, they think it's unacceptable, and then they stop the read. And so the curve sort of goes up. Okay, good. All right. So, question now is estimating the L spectrum. Okay, from the noisy reads. Okay, and the question is, whether the alpha spectrum is exactly recoverable as the number of noisy bits goes to infinity. So in statistics, when one asks this question, there's a term for this concept in statistics. Do people know what the term is? You want to know whether you can estimate something exactly as the amount of data goes to infinity. That's the most basic question that one can ask in statistics. In fact, this may have some connection to Alon, Professor Olinsky's tomorrow's lecture. Do people know what this term is called? Hint is somewhere on this slide. The answer is somewhere on this slide. It's on the forward slide. It's consistency, right? When you have a statistical problem, there are usually two questions of interest. At least two questions. One is, as you gather more and more data, will you get back to the ground truth eventually? That's sort of the most basic question you can ask. If you cannot even get back to the ground truth as the amount of data goes to infinity, then there's some intrinsic problem with the setup that you have, and you better work on it. And number two is the question of how much data you need to collect to get within a certain accuracy of the ground truth, right? So that's the second question. Here, I'm asking the first question because I'm looking at the L-critical framework, and therefore I'm looking at essentially I'm allowing the number of bits to go to infinity anyway. And now I'm asking you, instead of having clean bits of noisy bits, can I recover the spectrum? And my good friend Chi Xiaomei, who actually really spent some time here at INC, yes, he answered this question when he was visiting me last year. And his result was somewhat surprising, I thought, which is, yes, for all p, remember p, the parameter of error, substitution error, except p equals 3/4. Now, if he did not have this except p equals 3/4, then you know that he had made a mistake. Why? If you have 3/4, then your output has nothing to do with your input, right? Because your probability of error, then your output is independent of your input. Then you should not be able to get any information from the output. But if you can do that, then you have made a mistake. And what he said is that except for this degenerate situation, for OP, you can actually do it. Okay? Now, this should be a PSA question, because actually, it's pretty calculatable. But let me give you some hint as to how to approach the problem. How we approach the problem, I should say. Okay. So, all right. Now, what is the L spectrum? Right? Let's think about how to represent the L spectrum. How many length L sequences are there? How many length L sequences are there? A, G, C, T? It's a very simple question. No. It's 4 to the L. There are 4 to the L possible length L sequences. Sorry, this is a very simple question. All right? So there are 4 to the L of such sequences. Okay, so I'm going to list a table of all possible length L sequences. And on the right-hand side, I will write down the count. How many times do I see a particular sequence? For example, this may be a sequence of, I don't know, LX. Okay, I won't see it. But if I see it once, then I'll put a 1 there. If I see it twice, then I'll put a 2 there. If I didn't see the sequence at all, I'll put a 0 there. And now I have a whole table. Okay? So therefore, this table is my representation of the spectrum. Yeah, it's a very big representation, but still it's a representation, right? I'm just talking about information, not for complexity, right? So therefore, can I represent an L spectrum by our favorite MATLAB vector. A, we're in EE we're vector. Yes? So we have a vector which is the L spectrum. And this vector is what I want to estimate. Let's call this vector, I don't know, how should I call it? V. All right? This is the unknown vector that I want to estimate. But what I observe, what do I observe? Noisy version of that, right? And as I get more and more data, what do I get? What can I for sure estimate? Another vector. So hence, another vector U is what I can actually estimate for sure. Again, U has the same dimension as V. But now U is the number of occurrences of each of these vectors under the noise perturbation. Right? If you have gone through noise, you're taking these vectors and you're going through a noisy channel. And now there is a statistical fraction of times you're going to observe each of these reads. As you take more and more measurements, you can estimate the statistical fraction exactly. Right? So therefore, you have a vector U which you can observe as n goes to infinity. You have an underlying V that you don't know what it is. And now the question is, how is U related to V? Is it a nonlinear relationship? Or is it a linear relationship?
Add a honey ball around the center, around the location.
Yeah, that's right. And this matrix depends on the noise parameter P. I don't mean to use H, I should not use H. Let me use A. For information theorist, H is a bit safer. All right? So this A depends on P, and you can work it out. And in fact, you should work it out. And so, therefore, to find whether you can estimate V exactly as n goes to infinity is therefore equivalent to what? Equivalent to whether this 4L by 4L matrix is invertible. And what Qi Jiang showed is that this matrix is invertible for all P except P equals 3. Okay? And how do you show that the matrix is invertible? So I think that's the last hint I'm going to give. What's the simplest way to show whether a matrix is invertible? What is the determinant? It's 0. And what he showed is that the determinant is non-zero for all P except P equals 0. Okay? So it turns out that the determinant of the matrix can be explicitly computed. Okay? And this will be the EASIT question. Okay, good. Another question from EASIT. Okay, so the problem is consistent. So that's encouraging. What it means is that if I have enough read data, then my critical read length does not have to increase. However, after you get this result, then it becomes more ambitious, right? Because now you're interested in whether the number of reads you need, actually, is it much more than the noiseless case, or is it comparable to the noiseless case? And that was the question that we asked. Okay. So, at this point, I want to introduce a concept called coverage depth, which is a term that I do not use too much, but this term is used a lot in this area, so maybe I should mention it. Coverage depth is actually very simple. Coverage depth is basically how many reads on the average covers each position of the genome. I have a position on the genome and I look at all the reads that cover it, and I count how many reads on the average cover position, and that's called coverage depth. So here's a question for you. How does the coverage depth depend on the three parameters of interest, G, N, and L? And then when you do this calculation, coverage depth, C. The coverage depth. Does it increase with N or decrease with N? Increase with N, so let's put N in the numerator. Does it increase with L or does it decrease with L? Let's put L in the numerator. Does it decrease with G or increase with G? If I have a very long read, very long genome, will the coverage depth reduce or increase? Let's put G in the denominator. That's it. Coverage depth is N times L over G. And in this field, people are interested in figuring out how much coverage depth do you need. Okay? So what Qi Wang showed here is that it's a very strong result because he doesn't put any assumption on the genome at all. Okay? What he showed is that except for P3/4, essentially you have enough coverage depth that you can recover the noiseless result. But we want to ask a more ambitious question, which is, can I use the same coverage depth as the noiseless case? Or how much more coverage depth do you need in the noiseless case in order to get back the genome result? And we proved the following theorem. Our result is on the one hand weaker than Qi Wang's result. Because what we showed is that if I make a strong assumption that the genome is identically IID distributed, which as I showed was not a very realistic assumption. On the other hand, it does allow us to prove quite a strong result. Okay? What we showed was that if the read error rate P is less than a threshold, and this threshold depends on the IID statistics of the genome, then Lambda-Waterman coverage is sufficient for error-rate calculation. So remember, for the IID genome, we have just picked it, right? What was happening in the IID case? In the IID case, we have this asymptotic picture, is that you have coverage 1 here. This is impossible. Above 1 is possible as long as the read length L is greater. So yeah, this is your achievable part. Right? So that means that when your read length is greater than L critical, then coverage by Lambda-Waterman is sufficient to reconstruct a noiseless case. We basically show the same result in the noisy case. As long as P is less than a certain threshold PPR. Okay? So our result goes further than Qi Wang's result, but it's narrower because it's focused on the IID genome. Okay? Alright. So, what is this threshold, you may ask? Well, it turns out that for this threshold you can calculate depending on the distribution. And for the case where you have a uniform distribution that is 1/4, 1/4, 1/4, the threshold is 19%. So that means as long as the noise is less than 19%, which is a pretty big number, you can recover the noiseless result. Okay? Moreover, we showed that a very nice architecture, we call separation architecture, which is essentially error correction followed by an assembly, assuming the read is more or less noiseless, is sufficient to achieve this result. Okay? So let me finish off the lecture by explaining this result, because this result read in EASIT2014, so okay. All right. Okay. So why can we achieve the noiseless result even with the coverage depth or the number of bits the same as linear Waterman? In other words, we don't need n to go to infinity humongously. And here's the idea. So this is the picture of the coverage depth. Okay. Okay. Do anyone remember what was the number of reads required for linear Waterman? This expression is supposed to calculate, but do you remember what was the expression like? G over L, but with an extra factor, log G over L epsilon, right? Okay? All right? So, example, G, okay. So, what does this say about the coverage depth when you are using linear Waterman number? What's the coverage depth? So C, linear Waterman, is equal to what? Right? Remember that C, linear Waterman, C is related to NG over L by N times L over G, right? So therefore, C, linear Waterman is right? So therefore, there is a logarithmic term here, which is the linear Waterman. So for example, when G is 3 billion and N will say 100 and epsilon is 1%, this number could be, I don't know, maybe 20 to 30. I'll do a quick calculation. Around there, all right? Maybe 20 to 40, something like that. So which means this? Which means that linear Waterman basically says that I need a certain number of reads to cover my genome, right? But to cover the genome actually means that on the average, my coverage depth is pretty high. 30, 40. This is a typical number for the experiment. And in fact, some experiments even go up to 60, 70. So you may ask why? I only want to cover the genome. Why do I have so many coverage depths? It seems I'm providing a lot of redundancy. First, we need to understand why our coverage depth is suddenly so high, although our goal was only to cover the genome, because that was a necessary condition. If you understand why, when you collect coupons, you want to collect every single coupon. That means on the average, you're collecting most of the coupons quite a few times. You know why? Because imagine you want to collect all coupons, right? It's very difficult to collect the last few coupons. Because the last few coupons, you have to collect many times, because now you have most of the coupons. And you sample over and over again, you probably just get back the old coupons until you get really lucky and get the last coupon. So in the process of collecting all coupons, you're actually collecting most of the coupons many times. Okay? And so the coverage depth is high. And this provides opportunity, guys. Why? Because we know that when you have high coverage, when you have a read many reads covering the same position, then what do we have? We have redundancy. If we have redundancy, that gives you error correction opportunity. And therefore, it gives me potential of averaging the noise that hits each one of these positions. And therefore, will give me a reliable estimate of the underlying. And that is the basis of our result. I cheated. I cheated again. You guys let me off. What did I cheat? This picture assumes that I know that these bits belong to the same position, right? But hey, wait a minute. My original problem was to assemble these guys. My original problem was to put these guys back in the right position. And now I'm already assuming that they're in the right position. So obviously, I'm in a chicken and egg problem. You know chicken and egg problem? Chicken and egg problem means you don't know whether the chicken goes before egg or the egg goes before chicken. And here we don't know whether the assembly should go before the noise averaging or the noise averaging before the assembly. Right? It turns out that we can resolve the chicken and egg problem. It turns out that to align the bits together is actually an easier problem from an information point of view than the assembly problem. And here's what we showed. What we showed is that to figure out whether a bunch of noisy reads should be from the same location is actually requires a condition which looks like this. Finally, the mutual information occurs. This is the mutual information across a channel of parameter P. So this is some scope of information theory. So finally, the mutual information appears in the very last slide. Okay, sorry about that, but at least it appears. Okay? So I want to get my paycheck back here. So just want to make sure that note mutual information is. And we remember that assembly is possible using noiseless read if L satisfies another condition, which is 2 log G divided by Rene entropy of H times, right? That was the expression I gave earlier. So it turns out that this number and this number has some relationship. And it turns out that if P is less than, say, 19%, then this number is bigger than this number. Which means that if you could assemble, then you could also do multiple alignment. If P exceeds 19%, then this number becomes less than this number, which means that this approach doesn't work. In other words, this approach will affect the performance. Okay? So, this is the theory. But then I got another student who tries to implement this theory to build a real assembly, right? Because that's the goal. It turns out that there are several problems in implementing this. Right? One is if I want to do multiple alignment, basically I need to test whether M sequences. They should be close together. Computationally, this is really expensive. So what you need to do is to use a technique called fingerprinting. So there's a technique in computational biology where instead of looking at the entire sequence, you just look at a short subsequence. And if it's noiseless, so the hope is that although you have noise which hits some position, there may be a short subsequence which is noiseless. Using that as a fingerprinting, you can actually efficiently align these things. Two is, as we mentioned, real genomes are not IID. And the solution is we can just replace the greedy assembler, which works for the IID case, by multi-bridge. So by combining these ideas and applying some real data, we can actually assemble them. We simulated our assembler. And we show that our performance is actually pretty close to the low value in the noise system. Okay? So this is 4 genomes that we tried on. In all 4 cases, we see that our performance, these are the points in which our assembler works. We can see that using the number of reads and read latency is pretty close to low band. We can actually say. Okay? All right. So I think I'm done. I have like millions of slides left over. So I'm done. But before I do that, let me say, I don't know how I can move this thing here. Let's see if I can. Okay, let's go forward. So I'm hitting lunchtime now, I guess. So I missed out on the half the story, but that's what happens. So this half of the story is assembling RNA sequencing, which is a little more complicated. And I think I did not have time to do it, because at this point, we people are doing all of them. So I'm fine. Yeah, communication, transmitting information above sharing capacity is possible. The question is whether you can decode, whether you can able to decode above capacity. Okay, so these are all the people who work with me in this project. Bunch of folks work on DNA assembly, bunch of folks work on RNA assembly. I thought I'd show them because these are the people who actually do work. Okay, so CUHK connection. So Kit graduated from the math and IE program, I believe, and 4 other people have CUHK connection. I think that's it. one. Okay, cool. All right, so that's it. Thank you.
Questions from